So hello everyone. So as we have completed the most crucial part of machine learning, the mathematics is required for machine learning. That's the metrics and the related to algebra to metrics. Now we'll start with what's known as optimizations. Okay. So most of the problems that you'll see in machine learning or deep learning, they're posed as optimization problems. So if you, for example, see the logistic regression, linear regression that we did. In linear regression, what we try to do, we posed a problem as a minimization problem, minimize the errors. So we wrote something like this, minimize. Then we had a function like this, and then we put some constraints or something like this. So this here is called an objective function. So the function that we want to minimize or maximize, that's the meaning of optimizations, and you want to optimize somehow. Let me first give a broader context of optimization, then maybe we can turn on the functions and then we can cover the basics and we'll go on in that flow. So what do we mean by optimizations? So for example, let's take a real world example. If you want to optimize and optimally utilize your time, so you want to optimally utilize your time. Utilize your time. So how to do that? So first thing is you will come up with some things. You'll come up with, okay, these are the things that I need to do. So you'll come up with bunch of things, like let's suppose task 1, task 2, task 3 and task 4. These are things I should be doing. And then there's a constraint that I have only 24 hours for, let's suppose. And then you'll formulate this thing and try to optimize your time and try to see how I can maximally optimize, how I can maximally utilize my time. So we'll call that maximum optimization problem. And in the similar way, you can do the minimization problem. You can somehow try to minimize something. Let's suppose you're writing your algorithm. So in that you try to minimize something. So basically optimization means you want to either achieve a minimum of something or you want to achieve maximum of something. In maximum you might see, for example, you want to maximize your profit. Let's suppose if you are doing some business and you want to maximize your profit, that's called the maximum optimization. And in the minimum optimization you want to minimize something. Let's suppose you want to minimize the utilization of resources that you have in machines or something like that. So this is the broad generic view what optimizations mean. So then here in mathematical sense we have some functions which we want to optimize. So what is a function? Let's see first that what is a function, so that we everybody is on the same page. So I can't take things for granted that you know these. I think most of you guys know what is a function. So basically I don't want to define it mathematically in going into those sets and relation and things like that. I'll just give a brief notion of what a function is. So function is anything, it takes some input, it takes an input, and think it like a machine. It's a machine or sort of thing, and then it gives an output. Okay. So here multiple inputs. So if you have multiple inputs, let's suppose I have an input x1 and x2. Maybe in the output they can have similar output. Okay, here they have an output for example y1, but reverse is not true. So you can not have, for example, y1 and y2 over here, and this is mapped to x1 and x1 also. So this is not a function. So this is basically a function. Okay, briefly speaking, if you have some mathematical expression, okay, let's think it at a machine. So you are giving it an input and it's producing some output. So what I'm telling is this is allowed. So if you have some multiple inputs and they can be mapped to similar output, but the reverse is not allowed. So one input cannot be mapped to the two output. That's what a function means. So there are different types of functions and stuff like that. Let's take an example. For example, x square is a function. So if I write f of x is equal to x square, so that means if I give it value 1, so the output will be 1. So if I give out value 2, the output will be 4. If I give minus 2, it's again 4. So here you see that these two inputs they got mapped to 4. This 2 and this they got mapped to 4. Okay, so this is a function. So x square is a function. So many of the times you will write it like this: y is equal to x square. Okay, so this is a function. So this is briefly what I mean by function. And then what you have to do is you have to optimize these functions. You are saying that, for example, I want to achieve the maximum value of the function, or I want to minimize this function under some constraints. That's where calculus and these things are required. Okay, if now you have this background, let's delve into this calculus and why do we do it. My approach will be, if you were present at that time when the calculus invented, like Leibniz, Newton and other people who invented the calculus, so you should have sort of developed whole of the calculus yourself. That's my point taking these lectures. And I hope that after having today's session you will feel that yes, we can sort of derive these things ourselves. So if the problem that Newton and Leibniz were dealing with. If we have to deal with such problems, then we would be able to sort of solve these problems ourselves, and we'll be coming up with the tools. Let's start with a simple idea. Okay, so I'll first describe some more mathematical details, so that after that it becomes easy to understand any other things. So there are two concepts that I would like you to focus on. The one is called the concept of infinity. Okay, infinity, and then there is something called as infinitesimal. Spelling can be here and there. So infinity means, for example, usually you are saying that if something is very very large, so it tends to infinity. So basically infinity, the first concept I want to say, infinity is not a number. This is not a number, but basically it is a concept. Okay, it's not a number but a concept. Similar with this infinitesimal, so it's not a number, they are concepts basically. So what is infinity? If you say me, for example, if you give me the biggest number in the world, you say, for example, I'll put 10 raised power 100 or something like that. So this still is not an infinity. It's a huge number. Anything that you can count is not an infinity. Okay. So what infinity means, that you basically do not count. You cannot count it. It's just like a concept. So you're saying 1 divided by 0. Sometimes you write it as infinity. So this basically means this is not defined even. Why is it not defined? Because infinity is a concept, and we cannot sort of have a concept and make it as a number. Okay, so this is just a brief description of what infinity means. Infinity don't consider as a number. So if you write something like this, 1 divided by 0 is equal to infinity, this does not mean that infinity is a huge number. Okay, to just describe the largeness, or to sometimes quantify this largeness, how much huge a thing is, so we say infinity. Okay, so infinitesimal means, so if you have a number which is really really small, it's really approaching zero, something like this, 0.000, and you keep on putting zero, and at the end you put 1. So this number is not zero, but it is sort of tending to zero, but it is not actually zero. It's so small, you can say it is tending to zero, but it actually is not zero. So we call these quantities which are so small infinitesimal. Okay, so having these concepts in your hand now, so now let me see what are the problems that the masters of calculus, or the inventors of calculus, were dealing with. So I'll just try to sort of make these problems look like easy problems, and then maybe you can stumble on the tools. So let's start our journey with a circle. Okay, let's suppose this is the circle we have at hand. So as you know that the area of circle is pi r square. Okay, so why do we get this pi r square from? So okay, this is our question. So we want to find the area of circle. So that's a question in our hand. So if you want to find the area of circle, so what to do about this? So you can sort of, you have the circle, and you can try to break the circle into different portions, and try to come up with really a nice construction in which we can find the area. Let's suppose I'll say the first way you want to construct, you want to slice the circle is like this. You create a small slices of this. Okay, something like this, and then you can put these slices like this. You can put one slice like this, and the slice like this. So you're making something like this. So if you see, so here let's call this length over here, the length that slice size of the slice over here, let's say it's very very small. It is something called dr means it is going near to that infinitesimal, it is nearly extending zero, it's nearly tending to zero. So for that, what I'm saying is, the more thin these slices become, so this figure will become like a rectangle. So how many of you agree on this point? The more these slices the thin become, so for example, if I made it really thin, so it'll be like this, something like this. So it will go on, and you will see the more this dr approach to zero, and this will turn out to be a rectangle like this. So do you agree on this point?
Yes, sir.
So this will become like a rectangle. So if you make these slices infinitesimally small, like dr should be tending to zero. So for that, what I'm telling you is that, so now you know that each slice has radius r. So now that means that rectangle has this length of r. Now you see that some slices goes in here, and some slices go in here. So exactly what happens is, so there will be half red slices and half yellow slices. So actually if you want to measure length of this, so length of this will be basically half half of circumference of circle. Circumference of circle. Circumference of circle. Okay. So what is the circumference of circle? You know that 2 pi r. That's the definition of circumference, or that's the definition of pi basically. So here this will be pi r. Okay. And now if it turns out to be a rectangle, so what is the area of rectangle? What is the area? Actually, we want to find the area of circle. Area of circle. So we said that it's approximately equal to the area of this rectangle. Rectangle. So if you saw the area is equal length into breadth. So here we have this pi r multiplied by r. That's pi r square. So what are we trying to do is we are trying to first break down a large figure, a large, let's suppose, shape into smaller shapes, smaller shapes, and then what are we trying to do? Then we sum up these things. We sum up these things. Okay, so if you tell me how do we do it, we have a problem. So most of the problems that you will see in the calculus, what they basically boil down to, we have a problem and we break it down to this small sum of small sum of quantities. So that's what I told you. In here, each of this dr is nearly equal to 0. Is it clear so far?
Yes, sir.
Okay. Now I'll take another approach to break down this, to come up with formula, because I want to introduce you what is the meaning of differentiation, integration, and stuff like that. And now I'll again take the same circle. So what I'll do is I'll take this circle. This is my circle, and I want to find its area. So other way to break it down is I'll break it down like this. Let's suppose this is one circle, this is another circle. Okay, then this is another circle, and so on. So this circle basically is made up of concentric circles. So I'll call them concentric circles. Concentric circles. So what I'll try to do is now each of this. So if I take one circle like this, one circle. So thickness, I'll call it dr. The thickness of each of the circle, let's suppose dr, which is tending to 0. So I'm saying first take the smaller circle. Okay, then plus whatever is basically the whole circumference of that, add it to that bigger one, a little bigger circle. Okay, then plus a little bigger one. But I'm just telling you that this dr is nearly equal to 0. This dr is tending to 0. That's that infinitesimally small. It's 0.00001. Okay, and then I'm adding this to get the area of circle. So now if you see, if you flatten this circle out, if you flatten one circle out, what you will find is you will find something like this. You'll find a slice like this. Okay, so this is the slice that you will find here. This is the width. It will be dr. Okay, so do you agree that it will be like this? The more this dr is small, this will become like a rectangle. You are just opening the circle. So for example, you have a ring like this. Now what you do is you try to open it, you try to flatten it. So if you see with the wire, so that will perfectly be, if you have that rectangular sort of thing. So if a wire is flattened, so if you make it a circle and then you try to unfold it and you want to make it a wire like thing. So you have the circle and you try to make a wire out of this. You put a cut over here and then it will be like this. So if you see it in the at the zoomed in level, so you will find that it will be like this. So the more this dr is tending to 0, this will become like a rectangle. Okay, do you agree with this? This will become like a rectangle.
Yes, sir.
Okay, so the thing right now is that, so we are taking the first smaller circle, then bigger circle, so we can just plot it in a graph. So how I can do it? So just let me plot a graph like this. Okay, the first slice will be like this. Let's suppose the first slice will be like this. Okay, the second slice will be like this, a little bit bigger. Let me show it. First slice will be like this, second slice will be like this, a little bigger, it will go bigger. Okay, and it will go on. So we try to decrease this dr, so it will be a line like this. So let's suppose, so if we draw this, this will be something like, let's suppose like this. Okay, let me just draw them perfectly so that they touch this line, because now you know that you have the concepts of line. So this line is basically 2 pi r, this line. So why is it 2 pi r? Because if you take any point over here and you want to compute, because you basically are computing the area of this, so area basically is equal to the circumference of the smaller circle. So these are basically the smaller circles. This is a smaller circle, this is a smaller circle. So if you take any point onto this, for example, you take this point. So here, if you want to take what is the area of that, this is 2 pi r. Again, taking this point, this is 2 pi r. So what we basically want to find is area under this curve. So that this is what we want to find. So we want to find basically area under this curve. Here we have this line. So what we have done is we took this problem of circles. So I divided into concentric circles. Then I stretched these concentric circles, and then what I made, I just plotted a graph out of it. So this is the first slice, this is the second slice. Let's suppose the first slice, second slice, third, fourth, like this. Okay, these are the slices of those circles, things like this. And now we have this dr basically is the thickness of those things. So if you take any one slice, so its area will be 2 pi r. Okay, now if you see, let's suppose this is from 0 to r. So that's what slices are, because this we have radius r of the circle. So I'm saying that this is the first is with the 0 radius, then it goes out till r. That's what I'm doing. So I'm saying from 0 to r, these circles are there. So now if I want to find the area of this, now you see that this boils down to finding the area under this line. Okay, from 0 to r. If you see that this is a perfect triangle. Okay, so here to here the length is basically r, and here to here, if you see, if you want to find the height, this is just 2 pi r. Okay, then area of circle is then 1 by 2. This is base, that's r, into height, that's 2 pi r. 2 get cancelled, and this is pi r square. This over here is called as integration. Is it clear? So I don't want to have the symbols first. I want you to
Yes,
sort
sir.
of understand this, why is integration needed. So what are we doing is we are trying to break a problem into a smaller sum of many problems, and we want to compute the sum. Okay, sum of many problems. So we have any problem, so that problem gets boiled down to this sum of very smaller values, and then we try to calculate it, and that is basically the area under graph. So we have some problem. So what we try to do is we try to break it down as sum of small quantity, sum of small, but there are many values, sum of small values, sum of many small values, and this we can compute from the area under curve. Now the question is that here we have simple curve, we have only 2 pi r. So this curve can be even different. This curve can be like this. Let's suppose this curve can be like this. So we have a graph, and this curve can be like, let's suppose, like this. Okay, or if we talk of parabola, let's suppose this can be like x square curve. Okay, and we need to find area under this x square. That's why from this concept of calculus started. So we wanted to generalize this idea. Mathematics doesn't stop there. If you solve a problem, let's suppose we solved a problem of finding the area of a circle. So now the problem is we boiled it down to finding area under some curve. Okay, that's how I did it. So I took a problem, broke it down into smaller values. So after that, I tried to find some area under a curve. So I'm telling you that this is what I did for one problem. Now, if I want to generalize this idea, if I want to find some methods by the help of which I can find the area under this curve. So this is one of the curve. Maybe some curve can be like this. Let's suppose we'll have curve like this, and we want to find this area under that curve, and we want to find, let's suppose, this area. Okay, for that we need methods. Okay, and these methods were captured by Newton and Leibniz independently. Okay, and these methods made the foundation of calculus. For example, if you see where will this graph come? So this graph will come if you throw a stone. So initially what will happen is, let's suppose this is distance covered by a stone, and this is time, let's suppose. So you are picking up a stone and you're throwing it in the air. So what will happen is, initially the distance traveled by the stone will be 0. Then it will for example reach, let's make this graph like this. So it will reach, the distance computer will sort of continuously go on, and once it attains this value, so this will be a graph. So it will be sort of like a graph with some randomness. For example, it will let's say initially start slow, and then maybe it will taking pace or something like that. Some graph will be there. If I take example of a car running, so how will it happen? So if I have a car and I want to see its speed, so speed of the car, initially it will be 0, then it will go on. Okay, and at a time it will reach the peak, the speed will reach the peak, then it will slow down, and it will go to 0. So this is from, like, for example, here it stopped, the car stopped, and here the car started, and you see this is the curve which represents the velocity of car. Let's suppose velocity of car. So this graph, and if we want to find something, so I told you we can break it down, and we need to find sometimes area under this curve. Okay, and sometimes we can have different types of graph. I'm just giving you some examples so you understand this point. So now what I'm saying, let's deal with this x square, and then we'll see. Okay, so if we want to find this here, I think like I sort of gave the intuition behind the integration. Now I will give you the intuition behind the differentiation, what differentiation is. Okay, then we'll go deeper in differentiation, because that's what's required more than integration in the optimizations, because you will be more of the times you'll be differentiating something. So for example, let's suppose we have this curve which is x square. Okay, and I want to find, because we have to find this area. This is some area. Okay, so if I want to find this area, so what I'm interested in, the first thing is I will see on changing this x. For example, this is my x. So if I change this x slightly, so what's the change in area? So that I want to see. So this, let's suppose, is the change in area. Let's suppose I'll slightly increase this. So I'll see what is the increase or what is the decrease in area. So with respect to this x, so what is the change that happens to the area? So let's suppose area is a here. Okay, so I want to see how much this area will get changed if I have this, if I just nudge it with dx, if I just slightly increase the area or slightly decrease this by dx, so what will happen to the area? Basically what I want to capture is, I want to capture the rate of change of area, rate of change. With what rate will something change? Okay, right now we are learning, so with what rate are you learning? That's the thing. So I want to see the rate of change of area. Okay, we write that with respect to what? Because you are changing something and you are seeing the effect. So you are changing x over here, and then you are seeing the effect on the area. So that's what you are seeing. So you're trying to change this x, and you are trying to see what will happen to this area. So if I change this x slightly in the positive direction, if I increase the value by dx, how much will the area increase? That's the question you are dealing with. So I am trying to find difference in the area. We call that dA, change in area. Okay, so if you see what is the change in area, so change in area will be this much. So if you take this slice, so if I take this slice out, so this will be again like a rectangle. So the more this dx goes to 0, so this will be like rectangle. So here dx is this, and then we have its length as x square. Okay, so we can write this change in area will basically be equal to the area of this. So that's equal to length, that we have this dx, length and length multiplied by breadth. So this is x square dot dx, x square multiplied by dx. So this is what will give us the change in area. So if you want to compute the change in area, what will happen to the area? So this is how you'll get it. So now what you can do is, if you take this, so this is basically an approximation. So this thing will be approximately. So this is dA is approximately equal to x square dot dx. So the more the dx tends to 0, more accurate will this become. Okay. So I'll say, let's suppose area, when we had, let's suppose, slightly nudged, we see change in area. Let's suppose initially we had area of 2. Let's suppose the x was at 2. So then we'll slightly increase this by 0.0. We'll say area at t 0.0001. Okay, so this is the change in area. So area initially at 2 minus, let's suppose this is the change in area, and divided by how much change you did, minus divided by 0.0001. Okay, this is what gives me the rate of change. Rate of change. Do you agree with this? This gives me the rate of change. So this basically should be nearly equal to 2 square. That's what I'm saying. So dA is the change in area. So initially we had area at 2. Then what we had area at 2.0001, let's suppose. Okay, so this is the slight change in x. Slight change in x, if you see. Then what I'm saying is that I'm saying change in area basically is this much with respect to how much we change the x. That's this much. So this basically should be equal to 2 square. That's from this expression. If you see, this dA by dx, change in area divided by change in the x, is equal to x square. That's what I did. This is what I wrote. So if you say this dA by dx, this is what we call as differential operator, or we call it differentiation. Is the concept of differentiation clear, at least like graphically, intuitively, geometrically, what I mean by this?
Yes, sir.
Okay, so now I'll go into more details. I just want you guys to grasp this concept first, so that I can go ahead with the concept of differentiation, what it actually means, and how can we mathematically model everything that's with it. Let me just have some water. Let's tackle this problem of differentiation now. So if you see any textbook, there you will find what differentiation is defined at. It will define something like instantaneous rate of change. Okay, the first thing that I want to find, I want you guys to find is that this instantaneous and this change, they have a problem with each other. So what is the meaning of instantaneous? Instantaneous means at a particular instant, and change. What is meaning of the change? So if you see what is the meaning of change, change happens over a period of time. Let's suppose some of your friends, they meet you in class 12th. Now they'll meet you after, let's suppose, your graduation. So they'll say you have changed a lot, yeah. So that means change happens over some period. So here you are saying that change is happening at an instant. Okay, so this looks what's called as oxymoron. This is sort of contradictory to each other. So I'm trying to find a change, and here I'm saying instantaneous change, and change actually takes some time. So this should not be instantaneous then, and it looks paradoxical. So instantaneous and then change. So if you have an instant, how do you measure change? Let's take an example of car. I'll tell you. After this session, you will look these. You should at least look at these problems differently. So what do you mean by speed of a car? Okay. So what do you mean by speed of a car? Can anyone send me that? Don't give a mathematical definition. Just intuitively, what do you mean by speed?
So distance upon time.
So that's a mathematical definition.
Change in distance over time.
Again, change distance. So if you simply ask me if I want to compute the speed of the car, so I'll basically look at speedometer. So I'll see speedometer and I'll see what is that showing over there. So can you define speed at an instant? Okay. Can you define speed at an instant? Can you define it? So let's suppose a car is running and then you capture a photo of it. So what's the speed at that moment?
Instantaneous velocity.
No, I'm saying velocity or whatever you say. So I'm not going into those details of vectors and stuff. So I'm saying, let's suppose I'm telling you, can you measure speed at an instant or velocity at an instant? Can you measure it? So you yourself said that distance divided by time, we call it speed. So in an instant, do you agree that distance covered will be zero? In one instant, for example, if you capture the car right now, so the instant basically means no time passed. If no time passed, like if no, then it should be impossible for us to capture the speed. Like, do you see the contradiction? So
Yes, sir.
we say speed at an instant means the distance changed divided by the time taken. So, but I am saying that at an instant, what happens is distance won't be covered. Okay, and no time will be passed. So how can you do that? Now comes the concept of this infinitesimally small things. So what we try to do is, so if you see a speedometer, if somebody is at if somebody is working with these in the sector of cars and stuff, and they measure the speed of car, how actually they measure is they'll take a very small time, they'll take a small time window. So what will they do is, so they'll measure, let's suppose they'll take 1 second time window. Okay, 1 second. So at the initial this 1 second, they'll measure the speed. So they'll measure the distance. Let's suppose the distance till that point was, let's suppose, covered was 60. Let's suppose in 1 second the distance covered was 70. So they'll say change in distance is 70 minus 60. Okay, then they said in total it took 1 second. Then they call this like the speed of the car is 10. Let's suppose this is meters, 10 meters per second. So but this is not instantaneous. You see the change in happening over 1 second. So what if we do one thing? What if we can do, and what if we can decrease this time? We can decrease it so that it tends to zero. So this time is not exactly zero, but it tends to zero. Okay, and that time we'll capture the change in distance, and that we'll call as an instantaneous speed, if you see that. And if I make a graph like this, so if I make a graph of distance traveled, so let's suppose make a better graph. So initially, let's suppose car started and it's traveling with a speed covering the distance. Then this is what it stopped. So this is here, this is distance, here this is time. Okay, so this graph basically represents the distance traveled by a car. So if you see at this point 0, no distance was traveled. the more you go up and the more you see that the distance was traveled. If you see its velocity graph, so velocity will look like this. The velocity that I showed you, it will look like something like this. Okay, because at this peak time, at this time it had high velocity. That's why you see a lot of distance was covered. So if you see in this instant, for example, from here to here, if you see, so here to here, a lot of distance was traveled. You see this much distance was traveled. A huge chunk of distance was traveled because the velocity was more. That's what is the meaning of this graph. I think by now you should be expert in reading the graphs. So this is our velocity, okay, and this is our distance covered. Let's call this distance covered S of t. Velocity, let's suppose v of t, because both of these graphs are with respect to time, and this is t. Okay, I would have written it like d of t because d of t we write is a differential. So if you take any other slice, let's suppose I'll take an highlight. I'll take this slice. I'll take, let's with white. Let's suppose this is one slice. Okay, this is one slice. That the distance covered in that is, why is it erasing itself? Is something wrong? Okay, let's take this red color. Okay, I hope that this is visible now. So let's suppose we are taking this much, and in this is the change in distance. So if you see it over here, so this to this is the change in distance. Okay, if I zoom it a bit, let me zoom it. Let me zoom it. You see on this. Okay, so this much was changed. So if you see from here to here, so this is this over here represents. So this represents change in time, and this here represents change in distance. Okay, so if I zoom it further to show you like very clearly, so it's making like a triangle. Okay, the more you see over here, this won't be able to, you won't be able to see, so you'll be able to see like this. So here you have some triangle like this. So this is the change in time, delta t, let's suppose, change in time, and this is change in distance, let's suppose delta s. That's what we observed. So the more this delta t tends to 0, we'll call it, let's suppose, dt. Dt represents change in time. Let's suppose if this dt is tending to 0. So do you agree that this will become like, this will be a point now? So it won't be a triangle like this. So both of these points, this point and this point, will collapse onto each other. So if you take this, so initially this was some sort of a line. This was some sort of a line like this. More you come closer, this will become a tangent to this. So if I am saying like what is the change in distance, so I'll first cover these points. So this was like this, something was like this. So this was our change in time, this was our change in distance. So these were at two instants of time. So this over here was delta t. So I am saying that this delta t is now dt. Dt basically means the thing which is tending to 0, like very small. So do you agree that these 2 points will sort of come together now? Because now the time was like this delta t. So I'm sort of shrinking these 2 points. So if I bring them closer, so what will happen? So a small triangle will be made. Okay, and if I made it still further, still smaller, so delta t should be 0. So basically it will sort of coincide onto each other, and this is what the change will define. So if I take the example over here now, so a tangent line will be there like this. Is it clear? So what I'm saying is that, so in order to capture this change, capture the change, something happened. Okay, in order to capture the rate of change, so what I try to do is I try to select a small delta t, that is this dt, and I try to capture that. I got to know that this change in distance divided by change in time, this is how I capture it. Okay, and I called it a ds divided by dt. This is how I captured the small rate of change of distance with respect to time. So in that, what I found is that if you see over here, it is making an angle over here. angle theta over here if you see it. Okay, so angle theta, basically this is perpendicular by base. This theta, if it is making the angle, so we can call tan theta is basically equal to this ts by dt. This tan theta is capturing the rate of change. Is it clear? Do you agree with this, that this tan theta is basically capturing the rate of change of anything? Like in our case, it is change. It is capturing the rate of change of distance with the time. So how much time it's changing? Again, taking that example, let's suppose initially it was 20 meters. Then the rate of the distance covered was, let's suppose, 20 point some 0 1. This is the captured, and it was, let's suppose, covered in from 4 seconds to 4.001 seconds, something like this. This is the change in distance, delta s. This is change in time, delta t. So this is how we capture the rate of change. And this thing is nothing but a derivative. So that's why sometimes you will see rise or run. This is called rise, and this is a run. Okay, this is rise, and this is run. That's what captures our differentiation. So differentiation is a rate of change, but rate of change at an instant. So instant basically here means instant is a very small quantity. It is not zero, but it is tending to zero. Okay, so that's how the inventors of calculus tackle this problem of some quantity not being exactly equal to zero. That's what I introduced, the concept of infinitesimally small. So it's really small, but it's not actually zero. Otherwise, whole of the things will break. So this delta t should tend to zero. That's what we call the dt. So this should be dt, and we capture that rate of change. But still, you should understand this thing, that this is not instant. Like instant basically means zero, and we're trying to mathematically jiggle these things so that this delta t is tending to zero. It's not equal to zero actually. Okay, so if somebody tells me what is this ds by dt, then I'll say the change in distance, let's suppose s of t plus delta t, some time elapsed. Okay, some of the time elapsed, or this is the distance covered in that time, minus what was the original distance. Okay, what was the original distance? That was s of t at the instant t, and there change in time, that is delta t. Can I write it mathematically like this? How many of you agree with this, and how many of you understand it?
Yes, sir.
Okay, so here I can write this delta t basically tends to zero. This goes to zero. Do you understand this? Because this is the distance covered at t plus delta t. Let's suppose at 4 seconds, and here at 4.001 second, because we have this delta t. This is distance covered at t. T, let's suppose, was is equal to 4. Now this t plus delta t is, that's equal to 4.00001, and this delta t is, let's suppose, tending to 0. This gives me the change. If you see, if this delta t tends to 0, then change in distance at this time minus the change in distance at time t divided by total change in time. So this is change in distance in s divided by change in time in t. Change in s and change in t. This is giving me the rate of change. So over here you have the formula for differentiation. This is the formula for differentiation. So what I said, you two important things to remember. Tan theta gives us rate of change. Rate of change. So this rate of change is really important. So why is this rate of change important? So there are a lot of problems where you want to see what is the rate of change, how much the things are getting faster and how much it is slower, and what is the rate of, let's suppose you're learning something, what's the rate of your learning. Learning is basically a change. So learning with respect to time, and we can come up with a metric score. So okay, I think yesterday we had a meeting regarding our website. So if we want to see how much information was gained by, and how much intelligent is a person, so we can also come up with a metric like this. We can come up with a metric like uh, increase in knowledge over time, over some time. That can be, let's suppose, metric of intelligence. I think this is fair, plus something or some other thing. So but we can come up with a metric of intelligence. How much is there change in knowledge? This should not be negative though, it should be positive. So change in knowledge plus divided by time. So how much time it took. So if you see this relation over here, the more time a guy takes in grasping knowledge, so our metric says that he is less intelligent, because they are inversely proportional. So in a similar way, if he gains very high knowledge onto very less time, then he is considered more intelligent. And we can come up with metrics like this. I hope that, Rian, you are taking, because we have a problem to tackle in our web design. We have tackle a problem, that is we have to come up with a metric how much is a guy understanding. So if he's watching a video, so how much is he understanding. So we'll see how much is the increase of knowledge. So we'll ask him the upfront question first, so he won't be able to answer. Let's suppose after 2 seconds we'll ask him a question. So if he gave the right answer, that means in the 2 seconds he sort of learned this. Okay, then we can say this is the metric, and we'll see how much time will it take to answer him, and we can jiggle around with different metrics to come up with the understanding. Let's suppose not, this is not the metric of intelligence, let's suppose this is the metric of understanding, let's say. I want you guys thinking these lines. So if you have a real world problem, so Rian, do you understand what the problem was, which I discussed in the previous session when
Yes,
we
sir.
had the meet? The problem that we had is that if somebody is watching a video and we want to capture how much he's understanding, okay, and we want to come up with a metric for that. So here what I'm saying is that we can also use this notion of rate of change. Okay, so this was just a little bit digression, because we are designing a website in which we're trying to capture how much user is understanding a topic or something like that. So this is the first thing I want to understand. Tan theta gives us the rate of change. Okay, and then I said instantaneous basically means some dt. Let's suppose if it is time, some dt which is tending to 0. Instant basically means it is not 0, it is infinitesimally small, it's very small. Okay, this is the instant, and the meaning of instantaneous, this dt tends to 0. Okay, and then I said this is written by the symbols like this ds by dt, and sometimes you will find it like this s dash only. So I think these are the notations introduced by Leibniz. These are the notations introduced by Newton, if I'm not wrong. Okay, so Newton used this dashes, or it can be other way around though. So but these are two people, they tackle the problem and they independently discovered this, and they use different symbols, but the underlying concept is basically similar. Okay, then the formula that we got is, if we have some quantity and that is represented by, let's suppose s of t represents here distance traveled at time t. Okay, so we are saying, so change in distance upon change in time is basically equal to s t plus delta t minus s of t divided by delta t. And here the argument is that this delta t is tending to 0. This is really small. Okay, let's suppose our distance, let's suppose this s of t is represented by, let's suppose, x square. So we are saying that our car runs like this. So in the at 0, so it covers 0 distance. I'll make a table like this. At 0 distance traveled, this is distance traveled. So at 0 what happened is I'm traveling 0 distance. So at 1 I'm traveling 1. At 2 I covered the distance 4, something like this. So this will be increasing. So I'm saying that distance traveled is basically represented by this function x square. So what I told you is that I said that if I want to see what is ds by dt, ds by dt will be written like this: s plus delta t, s of t plus delta t, okay, minus s of t divided by delta t. Now you know that this here I can represent as with, because now I know s of t is x square, so I can represent this by t plus delta t square minus t square divided by delta t. So this I can expand. So here I can write it like this: a square plus b square plus 2ab minus t square divided by delta t. Okay, so then you see this and this got cancelled, this and this is delta t, this is delta t. Okay, so you see this and this got cancelled. So now what we are left with, we are left with 2t delta t plus delta t square. So here divided by delta t divided by delta t both. So here we'll get 2t. So if you see this, at the end we got 2t plus delta t. Now we know that this delta t basically is tending to 0. So the answer we got is 2t. So do you agree with this? So the rate of, if our distance s of t is represented by x square, so I am saying that this ds of dt is basically 2 of, this is represented by t square. Basically it should not be x square, it should be t square, because that's s of t. So s of x is x square, so s of t is t square. So here this should be t square. So do you agree that this is 2t? So how many of you understood the process? You see the process. I just used whatever I said, like change in distance minus the original distance divided by change in time. Okay, and then I did some mathematical calculations. I came up with this. So this was our original distance traveled. This is how the distance traveled was sort of modeled by a function. And then I said change in distance by change in time is basically 2t. How many of you agree on this? Like, have I committed any mistake? Do you agree with this? Everything? Is it fine?
Yes, sir.
Yes, sir.
That's why you say, if you have seen that x raised to power 2 d by dx, that's basically equal to, you just take this in 2x n minus 1, 2 minus 1, that's 2x. Didn't you find a similar thing over here?
Yes, sir.
That's why we call, if you give me some, for example, we say we generally use these formula and directly sort of try to memorize these formulas, but there is no need of memorization if you need this. So if you know what is happening inside, what is the meaning of actual differentiation, what's the meaning of these things, you can come up with these formulas. Okay, let's do one more thing. Let's suppose this s of t is, let's suppose now, equal to t cube. This is our function. So if I want to see the rate of change, so what I can do is s of t plus dt, I'll now represent as dt, minus s of t. This gives me the change in distance, this much, because this is distance traveled at time t, distance traveled at t plus delta t divided by change in time, that's dt. Now I know the whole of this is represented by t cube, so I can add d plus dt whole cube minus t cube divided by dt. So now if you expand this, so it will be a cube, and this will be plus twice t. So if I write the formula exactly, so what will it be? So let me see it, if I have written it. Basically what I want, why I'm doing this example, I want you to take one thing away. So that is, this t cube will get cancelled with this t cube, that's for sure. Okay, so what will remain basically is, so we'll have 2t dt square, something like this. Okay, then we'll have 2t, the first thing is this 2t dt, then we'll have other terms which will contain either dt, which will contain dt squares. Okay, so divided by dt, something like this. I only want to focus, I want you to focus on this term. This will be, this should be t square plus dt, and where is the pen, and this one. So this will be the term. So many terms will now contain dt square and stuff like that. So I want you to focus, because all of these, this and this will get cancelled. Okay, and then we will have these small quantities remain where we have this dt square. So if it is already 0.00001, okay, if you square it, it will become again very less than, and we can ignore these quantities, and that's what we are saying. So here we'll be only left with this bigger quantity. Okay, so this, the bigger quantity, will be basically equal to 2t square. That's why we call d by dx of, let's suppose x cube is 3, it should be basically 3, not 2, it should be 3. So we call it 3x square. Okay, so you expand this on your own and then see, are you able to arrive at this? Why are we just omitting these d squared dt square terms? Because we are saying that dt, it tends to 0, and then the whole point of this dt tending to 0 is that if you again multiply it with itself, it will again become a less quantity. That's why we can omit these things, and whole assumption is that the dt is very small. Okay, that's why we get this 3t square. Now I want to generalize this formula. Okay, if I want to take this, so for that I need you guys to know binomial theorem a bit. So if I have, let's suppose s of t is represented by t raised to power n, something like this. So I can write this s of t plus delta t minus s of t divided by change in, this is delta t, let's suppose this is dt and dt. This now can be represented as this equation, t to the power n, t plus dt to the power n minus tn divided by dt. So focusing on this term only, focus on this. So I'll write it t plus dt to the power n, basically means t plus dt n times. So in the first iteration, what I'll do is I'll take this t's only. Okay, so I'll write t to the power n plus. Okay, that'll happen one time. This is t to the power n. Then what I can do is I can take one dt and I can take other these t. So I can take t to the power n minus 1 and I can take 1 dt. So how many ways can I take it? So for example, I can take 1 dt from here. Okay, then rest t's I can take it from here. Otherwise I can take dt from here, and I can take rest of the t's from here. Okay, so there are n choices of choosing a dt. Okay, so this will be n times t n minus 1 dt. Okay, there will be some other terms as well, and divided by this dt. Now if you see over here, if you, this is the expansion of this term, so now I'll plug in this value. So have you understood this? So this is basically binomial theorem. I'm sort of showing you it in simplification so you understand it if you have forgot the binomial theorem. So you might have seen that in that we write a plus b raised to power n is basically equal to nc1 t to the power 1 this b to a to the power 1 b to the power n, and then you write plus nc2 a to the power 2 b to the power n minus 2 n minus 1 or something. This is initially, it starts with 0 though. It starts with nc0 a to the power 0 b to the power n. So if you remember this formula, so what I'm trying to do is I don't want you to remember this formula, so I am trying to tell you. So if I want to expand this a plus dt, let's suppose I want to expand a plus b whole power n. So what I'm telling you, this basically is a plus b multiplied by a plus b multiplied by a plus b and so on till a plus b n times. So the first term that will be, because if I have to multiply, I'll take one term from this, one term from this, one term from this, and keep on multiplying. So if you know how to do a plus b into a plus b, so what you do is first you multiply this term with this, multiply this term with this. So basically from each bracket you take one term and then add them. Similarly I'm doing, I'll take for example a's from everyone first, so that will be a to the power n plus, then I'll take 1b from any of these and a n minus 1 and 1b. So that I can do n ways. So I can take b, 1b from here, 1b from here, 1b from here, 1 from here. So I can take these terms will be basically n terms. That's what I wrote here. So if this is clear now, so I can just erase it. So I said the terms that I'll have is t to the power n plus n t to the power n minus 1 dt, plus now I'll have some other terms which will have dt square, dt cube and stuff like that. I'm not interested in these terms because they'll anyway go to 0. So I'm interested only in this. So now I'll put the value over here. So what I'll get is, I'll get t to the power n, let me write it with different color, t to the power n plus n t to the power n minus 1 dt minus t to the power n divided by dt. So now this and this will get cancelled, this and this will get cancelled, it will be nt n minus 1. That's why we write d by dx of x to the power n is equal to n x n minus 1. Is it clear?
Yes, sir.
Okay, now I want
Yes,
you
sir.
to, I don't want you to lose the connection. So okay, let's suppose we have this d by dx of x square. So we did it in the mathematical notion. Okay, I'm trying to see the change. So this x square I can also represent as a let's suppose I'll represent it as a square. Okay, it has x and x. So what is the meaning of this? So because you know the x square is equal area of this, area of whatever you call, area of, let's suppose we'll call this figure a star figure, area of this figure. Okay, and this is represented by x square. So this is asking me what is the change in area if I have a slight change in x. So this question basically now boils down, this thing tells me intuitively change in area of square, change in the area of square, in the area of this square whatever we have, divided by change in its side. So this basically tells me if I nudge this side, if I increase the side a bit, let's suppose this is dx, I increase it by dx. Okay, so what will be the area in change? So I'll increase dx from here, I'll increase dx from here. Okay, so this is the change in area, basically this much, here it'll increase this much, so here it'll increase this much. So this is the change in area. So if you see this much and this much, so it will have, this is our dx change, so this is our x. So we have three pieces. If you see, we have this one piece, and then we have this other piece, then we have this smaller corner piece. This is the change in area. We'll call it, let's suppose dA, area change. So do we agree that we have these three pieces? One is this till this. Okay, the other is this in area. Then we have this corner part. Let's have corner part of blue. This is this. So do you agree that if we just nudge this dx a bit, this is the change in area? Do you agree with this? Show me thumbs up or thumbs down.
Yes, sir.
You agree with this? Okay. So here we have this dx and this is our x. This is dx and this is our x. So on the both sides, this is dx and dx. So now this is the rectangle. So this is basically x dx plus this is again a rectangle x dx. Okay, and this is dx square. Now you know that this is very small, this is a very slight change, but if you just add these two things up, this is 2x dx. Okay, and the change in area basically is change in area is equal 2x dx. With respect to dx, you can divide that dx, so again you will get 2x. That's why you got this x square. Now I'm seeing it as a square, so I'm saying this d by dx of x square basically is the change in area of units if you have this square. Okay, it has x and x, so if I make a slight nudge, so this will be the gain in area. So there will be three pieces, this piece, this corner piece, and this piece. So that is 2x dx change in area divided by how much we nudged, that was dx, and that's why we got 2x. You have to have this picture in your head. What are we computing? Differentiation is not like you're computing something else, somebody will give you a huge formula and stuff like that. This is a notion that I want you guys to have. Let's suppose, what is the cube then? What is this? D by dx of cube, x cube. So how you can imagine it basically intuitively is like this. If you have a cube, like this, okay, with each x and x, so its area will be x cube. Okay, so slight nudge in the area. So if you slightly change the side of this cube, so there will be the change in area. D of a divided by d of x will be d by dx of cube. So if you see the area, you will see that you will gain. For example, let's suppose you will increase this area a bit, so you will gain over here, and you will gain, for example, some area onto this side and some area onto this side, and you will gain the area exactly that will be equal to 3x square. This will be the total gain. This will be the total gain you will get. And then when you divide it by dx, so you'll get this 3x square. So this is the rate of change. So rate of change in area of this cube. X cube basically means cube. That's why they are calling it cube. Now do you understand why we call x square a square? Why we call x raised to power 2 a square? So we call it square because it represents the area of square. It represents the area of square. X into x square. We call this x cube. Why do we call it cube? Because it represents the area of cube. So if you see like how the mathematical legends and how these inventors use these terms, it will be pretty clear. So now we have a level of abstraction, and we just try to learn the mathematics without thinking in the detail. Why did it come from? So what is the real motivation? So now you know that why is this called a square? Why is this called cube? Why? Because this basically represents area of a square having length x, having the sides x. This represents area, or maybe less of a volume of the cube, which has this length of x, length, width, and breadth of x. So is it clear?
Yes, sir.
Let me guys give you some homework which you will do. So what do you want to do? If I want to differentiate d by dx of sine x, well, let's suppose sine theta. Okay, y is equal to cos theta. Now you have the requisite tools, you have everything that you need to sort of arrive at this result. So for that you must know the definition of sine x. So that I'll tell you. So what is basically the definition of sine x? That I'll tell you, and then we can move. So do you know that trigonometry is what is the meaning of trigonometry? Let's again take a detour. We'll take some digression so that you understand things better. So what do you mean by trigonometry? Trigonometry. So in that you mostly have heard about, you read about triangles and stuff. Rian, is it the safe way to say कि most of the things that you read in trigonometry is about triangles?
Yes, sir.
So actually trigonometry is more about circles than triangles. You know why? Let me show you. So if this is the circle, let's suppose. Okay, and this is my center point. So usually you might have seen how do we define the sine and cos theta by triangles. So we say that if we have a triangle, this is our perpendicular, this is our base, and we say sine of theta. So if this is theta, this is perpendicular by, this is hypotenuse, let's suppose h, this is perpendicular by hypotenuse, this is cos of theta, then we have base by hypotenuse, then we say tan theta, p by b, let's suppose. So this is what you write generally. You see the triangles. Actually what happens is, how do you know that cos of, let's suppose, 90 degrees equal to 0? How do you know that? Or how do you know that sine of 90 degrees is equal to 1? So how do you know this? Okay, so let me tell you that, so that you will be able to derive this homework. So if this is a radius, let's suppose unit circle radius. Okay, So if you traverse a distance, let's suppose some distance over here, you traverse something over here, so you land it here. Okay, so you land somewhere over here. So now you covered, if you see over here, so this is unit circle, let's suppose the radius is equal to 1. You covered something over here, so this you covered. Okay, now if you increase, if you cover this much, so you'll have this. If you covered, for example, this much, I'm seeing on the this r. If you see that, if you see this, the distance the distance that you are covering from here to here, and then if you draw a perpendicular onto this, onto basically the horizontal axis, so what it gives you is, it gives you cos of theta or sine of theta. So we'll have to check that, because this over here is 0, so then we'll have 90 degree. This gives cos of theta. Okay, so if you want to measure cos of theta, so if somebody says you, okay, what is cos of 90, so you'll say, I walked 90 degrees. I walked from here to here, so this much I walked on the circle. So okay, then what is the perpendicular onto this radius? It's here, it's 0. That's why cos of 90 is 0. So but if you sort of measure the horizontal distance, that is this distance, let's suppose this again is a radius, this is also a radius. So if you measure this distance, let's suppose you covered this much of distance, and now you're measuring the distance onto this. This is sine theta. If somebody says you, like, I covered 90 degree distance, so 90 means this much. Okay, so that's again, if somebody says that, what, like, we know that sine of 90 is equal to 1. Okay, you covered the 90 distance, this much of distance, and now you draw this onto this, and you will be here, you will be landing at this point. So initially, if you have distance over here, you will be landing at this point. If you here, you will be landing at this point. So that's why if you see sine cos at 0 is 1, cos at 0 is 1, so it will slowly decrease, decrease from here. So that's why if you take rounds of the circle, so from here cos was initially 1, okay, then it slowly decrease, reaches 0, at this point. Let's suppose we have this graph like this, it will slowly decrease, it will reach at 0, reach here, it will reach 0 at here, like I'm speaking about cos theta. So after that, what will happen is, when you will try to again traverse, it will again increase, because now it will be traversing this, but in negative direction. That's why it goes negative. So when you reach here, again it will reach this 0. So it will again reach till here, it will reach 1 here, so here it will be 1. So if you see, but negative 1, okay, and then it will again start decreasing. So this will go like this, because you are just rotating on the circle. You are starting from here, going till here, then coming like this. So that's why this graph is like this. This is for cos theta. What is for sine theta? So if you see the graph of sine theta, so what will it like be? So sine theta, basically I told you, you are traversing a distance. Let's suppose from here, how to measure the sine theta is you drop the perpendicular onto this, So sine theta now is 0. Slowly, if you keep on going up here, the distance will keep on increasing. Okay, it will get a 90 degree maximum value. So that's why you get 90 maximum. Then it started decreasing, goes to 0. Again, in the negative direction, starts increasing. This is like this. So do you understand the graph? Where do we get the sine theta and cosine theta from?
Yes, sir.
Now the homework is the rate of change.
Yes, sir.
Now you will have to see the rate of change. Now you'll have to see rate of change basically means, if I change this theta a bit, so I'll change it by delta theta. So what will happen to this cos of theta? What will happen to sine theta? You'll have to find that why is it d by dx of sine theta, or d by dx of sine x. Basically it should be d by d theta if I'm talking about theta, because we are seeing it with respect to theta. Why is it equal to cos theta? Because I think I gave you enough background now to sort of cover this thing. Now what we'll do is, we'll go to some rules, and then I'll try to also show you some visualizations of the rules maybe. So what is time? 7:54.